All right, let's get started here. Okay. Slides won't move. All right. So the last time we have been discussing about index data structures, more generally about how the data is set up on hard disk in order to make access efficient. In order to work with the data, we first of all have to bring it into main memory. More precisely, we even have to bring it to the processor. But today we're going to talk about how we bring the data into main memory. And there's one component in the database system that is the buffer manager, which controls data movements between hard disk and main memory. And moving the data is necessary in order to compute with it. Now, the relevant chapter in the Ramakrishnan and Gerke book, that is chapter number 7.4, we're going to first discuss about the buffer manager, and then later today, if we still have enough time, we will start discussing about the query processor component. So let's first chat about the buffer manager. Now, the buffer manager generally decides when to move data between hard disk and RAM. The buffer manager tries to be smart about that. It tries to minimize the number of data movements. And for that, it uses a couple of heuristics. We will see one of them in order to try to estimate which pages are most valuable and should be continuously stored. The name buffer manager connects to the term a buffer pool. And the buffer pool, that is an area in main memory that is reserved for the database management system. So this buffer pool, it is essentially divided into so-called frames. And those frames, they essentially, they have enough space in order to store one of those pages. And the page that is generally the granularity at which we receive data from hard disk. So the buffer pool contains lots of slots, those frames where you can store pages, and it contains some metadata about each of those slots. Now, here you see an illustration of the buffer pool. So the buffer pool essentially gets requests from higher levels in the database management systems. And those requests, they are about specific pages. So once the buffer manager receives a request for a specific page, it needs to make that page available in main memory. The buffer manager stores pages in the buffer pool that you see here. At any point, some of those slots, some of those frames might be empty, while others are used up by a page. So when getting requests, the buffer manager would first check whether the corresponding page happens to be already stored currently in the buffer pool. And if not, it will fetch it from the hard disk here. Now, the buffer manager stores some metadata about the content of those different frames. And it also uses internally some heuristics in order to decide, for instance, which pages in the buffer pool to erase in order to create space, and which other pages to keep. So that is the replacement policy. And we are going to discuss about the metadata and about the replacement policy in the following. Now, those are the properties that we store about each of the frames. First of all, of course, we want to store the ID of the page that is currently stored in the frame, if any, because that allows the buffer manager to match incoming requests for specific pages to frames in which the corresponding page is stored, if we are lucky. Also, we store for each of the frames a so-called pin count. The pin count essentially tells you how many processors, how many clients, so to speak, are currently using the content of that frame. And if there is still people using the content of the current frame, then that prevents us from erasing it and replacing it with something else. So the pin count serves as kind of a safety guarantee that people don't suddenly have a page erased that they are currently working with, right? So we can only evict, meaning prune out from the buffer pool, those pages where the pin count has reached 0. Also, we store a so-called dirty bit for the frames, for the pages that are stored in those frames. And that dirty bit essentially tells you whether the in-memory page was changed since it was loaded from hard disk. And that is important because changes in main memory are generally volatile, which means that they don't persist if power suddenly switches off, for instance, or of course, if you erase the corresponding page. And the dirty bit essentially tells the database management system that there is some changes on a page which would be lost immediately if the power suddenly switches off. And it also tells us that if we want to erase the corresponding page, then in order to make the changes persistent, we first have to copy the current page to hard disk in order to overwrite the original version of the disk of the page usually. Right? So the dirty bit tells us whether there's any changes that we need to back up before we can erase the corresponding page. Now, this is the algorithm that the buffer manager essentially executes. Whenever we have a request for a specific page, then the buffer manager first of all checks whether this page can be currently found in the buffer pool. In that case, we call it a cache hit. This is case number 1 here. And in that case, it is actually pretty short. What we have to do, we just increase the pin count for that page, meaning there's like one more process interested in that page. And then we simply return the address of the page to the requestor, and then the buffer pool is done. So that is the efficient case. Now, if we have a cache miss, which means that the requested page is not yet stored in a buffer pool, then things become more expensive. The first thing the buffer manager needs to do in this case is to choose a frame for replacement. Of course, in principle, it could be that we have certain frames that are currently unused, that are empty, so we can simply copy a new page into them. Now, when running your database management system for a while, then that is atypical. Typically, your entire buffer pool is taken up. So in choosing a frame for replacement, you're essentially saying that the current content of that frame seems non-interesting, and it can probably be deleted. So that is an important decision for performance, which frame you want to replace. And we're going to discuss more about that on the coming slides. Now, after we have selected a frame for replacement, we have to check the dirty bit, because it could be that the current content of that frame had some changes which haven't been persisted to hard disk yet. So if that dirty bit is set, then we first of all need to write the current frame content back to hard disk. There's one question here in the chat about whether a frame can have more than one page, but those frames, they are chosen in size such that they store precisely one page. So you can have many frames, but each of those frames typically stores only one page. All right, and the address of the page that is returned, yes, that would be often the address of that corresponding memory location. All right, so now we potentially had to write the page back to a hard disk in order to persist the latest changes. After we have done that, we read the requested page from hard disk, and then we write it into the frame in the buffer pool. And still we need to increase the pin count in order to make sure that this page is not suddenly evicted. And finally, again, we return the corresponding address. So this is the algorithm that the buffer manager executes. At this point, you might be wondering whether we couldn't use functionality offered by the operating system. So if you have ever taken an operating systems course, then you will probably have talked a lot about caching. So there's some functionality in the operating system that does something a little bit similar. So the question is, why do we need a specialized component for the database management system? And there's two principal reasons. The first reason is that the database management system has often very specific access patterns. You will see in the following that the generic strategies by the operating system often don't work so well for database management system. So a first reason is efficiency. The database management system is particular in its access pattern, so we probably want to implement a specialized buffer management strategy. Another thing is that the database management system makes very strong guarantees to users about having data secure, even in case of a server crash. And in order to make those guarantees, which we'll discuss in much more detail later, the database management system needs very tight control over when pages are written back to hard disk or loaded from hard disk into main memory. So it needs very tight control over that in order to make those guarantees. And that is often not offered by those generic components. Now, for instance, to make that a little bit more concrete, one very popular replacement policy, that's the following one. We call it the least recently used replacement policy. So in general, what you ideally want from the buffer pool manager's perspective is to always replace those pages in the buffer pool which will not be required for the longest amount of time. So you want to drop those pages which will not be required for the longest amount of time. That, of course, is difficult to predict in general. So we typically use heuristics, for instance, by saying, if I haven't accessed one page that is currently in my buffer pool for a long time, then I am unlikely to do so again anytime soon. So that is the least recently used heuristic, and it essentially means that if I have to decide where to create space, for instance, in the buffer pool or somewhere in memory in general, then I'm always deciding to override that page which hasn't been used for the longest amount of time. So that is the least recently used heuristic, and it is a very popular replacement heuristic used, for instance, by operating systems. Now, one case in which that one works badly, and unfortunately, that case is quite common in the context of database management systems. That is cases where I repeatedly scan the same pages. Now, that might seem strange because why would you read something again after you have just read it? But there is common cases in a database management system where you want to do exactly that. For instance, if I'm joining together the relation, the table with the students and the table with the enrollment information. So I'm searching for enrollments matching the students. Then one popular way to proceed would be to first load one chunk from the students table into main memory, and then iterate over all the pages of the enrollment table in order to find matching pairs. And once we have done that, then we load the next chunk of data from the students table and again iterate over the pages in the enrollment table. Then we take the third chunk from the students table and again iterate over the pages from the enrollment table. So this is a case where we will keep iterating over the pages in the enrollment table multiple times in a row. And here, if we keep repeating essentially in a cycle over the relation, over the pages in the enrollment table, It means that the page that I have not accessed for the longest amount of time is always the page that I will read next, because I'm essentially doing a cycle in the enrollment table. And because of that, always deleting the page that I haven't used for the longest amount of time is of course highly suboptimal. That is what the least recently used policy does. So this is just an example for a policy that seems perfectly reasonable in general, but that sometimes works very badly in the context of database management systems. So this is a common access pattern for database management systems, and the interplay between that pattern and this policy, the least recently used policy, that is also called sequential flooding. Okay, and here I have one more question in the chat. What happens if the buffer gets full and no frames can be evicted? Will reads come directly from disk? That is a great question. So there might be a situation where I have a pin count greater than 0 on all my pages in the buffer pool, and then I still have some requests coming in. Frankly, in those cases, it depends on the implementation, but often the database management system would just essentially reject any further work until the memory situation improves. Right? So, I mean, in the end, you always need a little bit of space in main memory to store those pages from hard disk. And if you currently don't have main memory, then you probably want to first process the current tasks before you accept new tasks. So the database management system would often reject further requests. All right, great question. And here, with this example, sequential flooding, we essentially see by using generic buffer strategies for replacement does not work very well in the context of database management systems. All right. So that was a high-level overview of the buffer manager, which is the component that connects the hard disk to main memory. Now, in the following, we're going to start discussing in a lot of detail about the query processor in this and in the following lectures. This is the component here encircled in red, and the associated chapter in the Ramakrishnan and Gyarke book, that is chapter number 12. So at a high level, this is what happens when a database management system is processing an input query. So first of all, your input query is parsed, meaning it is internally translated into a tree representation. And then the database management system uses a couple of heuristics in order to simplify that query. This is what the rewriter component does. Now, the query optimizer is more sophisticated than a rewriter. It also changes the query in order to make it more efficient, but it does so using much more sophisticated methods. In particular, it typically tries to predict the execution cost of different plan alternatives, and then it selects the cheapest one. We will discuss about this in much more detail later. After we have selected a processing plan for the input query, we forward it to the execution engine, which executes it step by step in order to produce the final query result. Now, those query plans that are processed by the execution engine, they essentially describe how data is generated. They describe that process step by step. We typically represent them as a tree, where each leaf node of the tree corresponds to a data source, to a table in our context. The inner nodes of the tree, they represent operations, and the tree edges connecting different nodes, they essentially represent data flow. The inner nodes in the query tree correspond to operations, and in order to process data, database management systems use a fixed set of standard operators. Each of those operators consumes one or two, in case of joins and some others, relations. And the output produced by an operator is also a relation. So this is why you can compose those operators, because the inputs are relations and the outputs are also relations, aka tables. So that means we can flexibly compose those different operators together into a tree. Now, a couple of standard operators that we will be discussing more about is, for instance, the so-called filter operator, which is typically abbreviated by the Greek letter sigma, and that one simply discards rows based on a condition. So it checks for each row whether it satisfies a condition, and if so, it keeps it, otherwise it discards it. Then we have the projection operator, and that one discards columns from a relation. And we have the join operator, which combines two relations by finding matching tuple pairs based on some condition, and so on. So this is some of the operators that we will be considering. And this is an example for one of those operators, for one of those query plans represented as a tree. On the right lower corner of the screen, you have the associated query, which essentially combines students and courses over the enrollment information and restricts the focus to the CS 4320 course. And finally, it only wants to retrieve the names of the students which are enrolled in that course. So the data flow always goes from the bottom of the screen towards the top of the screen. So in order to evaluate this plan, we would essentially start with the leaf nodes, which correspond to tables that are already available in my database management system. So here, for instance, we can start with the courses table. And the first operation that is written here, that is this sigma operator with the condition written as subscript c.cid equals CS4320. So we are restricting ourselves to the course with that course ID. And as we have seen before, this little sigma over there, it represents a filter operation. So after this operator, we will discard all the rows which don't have the course ID 4320, right? Now, the output of the filter operation that is essentially coming out of the top of that operator box in the plan, and it is fed into a join operation together with the enrollment table. So this is a join operation, therefore it requires two inputs, and here we are joining those CS4320 course entries with the enrollment table. And the result of this join operator, that will be the pairs of matching tables. So here essentially I'm retrieving enrollment information for the CS4320 course. The next operation is also a join again. Here I'm joining enrollments with the associated students, and the input to that is the enrollment information for CS4320, as well as the information about all students. And the output of that join will be a pairs of students together with one CS4320 course they have enrolled in, basically. So what I'm ultimately interested in is only the names of the students who enrolled in 4320. So the final operation, the root of this plan tree, that is a projection operation written as this P. There I'm essentially discarding all columns except for the one that I have selected here, which is the student name. And therefore, the output of that plan is the names of the students enrolled in 4320. And that would be one out of many possibilities to answer the query below. There's different possibilities. For instance, we could change the order in which we apply the joins, or we could maybe do the projection. Okay, or we could, for instance, do the filtering later in the plan tree. So there's different possibilities how I can process the query. All right, and whether there's some question in the chat about whether there's operators for adding columns or rows as well. So of course, your database management system internally has some operators in order to add rows. It also has operations that allow you to add the columns to a table. But in the following, we're gonna first of all focus on processing queries which do not change the data. Later in the course, we will also discuss transactions which might actually update your data. And there's a couple of new issues that arise in this context. So we will discuss about that. For the moment, we only discuss about queries that analyze your data. Great question. All right, so this is an example query plan that I wanted to show you. Now, the mathematical foundation for those query plans, that is called relational algebra. I'm not going to discuss relational algebra in too much detail, but I want to point out that connection. You can also find more details in the Ramakrishnan and Gerke book. So essentially, relational algebra is a mathematical version of those query plans. It essentially represents a query plan as a mathematical expression. And just to show you how we would represent a plan like the one we have seen before in a relational algebra. So this plan that we have just seen, if we want to represent this as a relational algebra expression, this is how it would approximately look like. So those relational algebra expressions, as you see, they use the same symbols for the operators that we have also used in the plan tree. They are, in a way, a more concise way of representing those plans as expression rather than as tree. The semantics is that we start evaluating those expressions from the inside, and then we work our way towards the outside. So here we would first start with one of the innermost expressions, which would be this filtering operation applied to C, which is the courses. Then next would be, for instance, next would be the join on the course ID, and then we would join the result of that with the student ID, and finally we would apply the projection. So it's the same thing, but represented differently. So I'm not going to go too much into detail, but I wanted to show you one relational algebra expression at least, and explain how that relates to query plans. All right. Now, this was a high-level overview of query processing. Now, in the following, we're gonna discuss a little bit more about the different components of the query processor, and that will keep us busy for a couple of lectures. Now, in the following, we're gonna start talking about the execution engine, because in order to understand, for instance, how the query optimizer makes its choices and so on, you first need to understand how query plans are processed in the execution engine and what the performance trade-offs are. All right. Now, the first thing we will be discussing about is how we can actually implement those standard operators that we have just seen. I told you that database management systems, they use a set of standard operators in those query plans. And typically for each of those standard operators, like the join, for instance, you would have not one implementation, but many alternative implementations. And this is what allows the database management system to choose in each situation that implementation which is most efficient, right? So that is the reason why you want to have different implementations. For each case, you have an implementation that is just right for that specific case. So we will discuss about a couple of different algorithms. We will also discuss about how to estimate the processing cost for those algorithms, because some of those algorithms that we will be discussing, they might seem a little bit unusual at first. And in order to understand why they are designed the way they are designed, we need to discuss about how we estimate the processing cost for those operators, because otherwise those algorithms won't make sense. So we will discuss about the implementation and about cost estimation. We will use a very simple cost model in the following. It is simply based on the number of pages that need to read from hard disk in order to execute an operation. Now that is of course a simplifying, but it is quite reasonable in the context of traditional database management systems, because there we assume that your data is mostly stored on a storage device like a hard disk that is actually quite expensive to retrieve and to store data. And that means that the main processing overhead in practice is often the overhead of moving data from hard disk into main memory. You might also have some overheads due to the actual processing, for instance, but data movement overheads often dominate total processing cost in those situations. And that is why we will simplify by estimating cost as the number of pages that have been read or written to hard disk. The first operator that we start discussing, that's the filter operator. The corresponding algorithms are simpler than, for instance, for the join algorithm, but we will see that there's already a lot of different ways of executing a filtering operation. So in general, when we filter, we want to retrieve rows that satisfy a certain predicate. And a priori, there's different ways to go about that. The simplest possibility is that I just scan all pages of the corresponding table. And for all the entries on each page, I check whether they satisfy the predicate or not. If they satisfy the predicate, then I add them to the output. That is the simplest alternative. Now, if I know, for instance, that my data is sorted according to a column that appears in the predicate that I'm interested in. For instance, I'm searching for information on one specific course, and my data is sorted by courses. Now, if that is the case, I can typically do something smarter, and I can apply some kind of binary search, as we have already quickly discussed in the lecture on indexes. I can use some binary search in order to quickly identify the page on disk where the information, where the first entries for the course I'm looking for are located. So that is often already more efficient. And of course, if indexes are available for the right table and for the right predicate and the right type of index, all of that, in those cases, I can use indexes in order to find the data faster, depending on the properties of the data and of the index. All right, so that is the high-level outline. In the following, we're going to make that more concrete and estimate processing costs for those different alternatives. Now let's start with a simple, or with an example here. So what we want to do is to retrieve enrollment information where the course ID equals 4320 again. Now, in order to get a hang of a cost estimation, I give you a few minutes in order to try to figure out how we can compute the cost for scanning the enrollment relation. So that would be the simplest way for executing this filter operation. Now, here on the upper half of the screen, we have a couple of numbers that are helpful in order to calculate that. For instance, we have the number of students given, we have the number of enrollments per student, we have the size per enrollment entry, and we have the number of bytes that we can use per page. Now, take a minute to think about how you would fill in those fields on the bottom of the page. In the end, the goal is to estimate the scan cost. But in order to make it a bit easier, I have essentially given you a different intermediate numbers that you probably want to calculate in order to get there. So I first would calculate the number of entries that you can fit on one page, and derive from that the number of pages of the enrollment table. And from that, you can quite easily derive the final cost. I'll give you a minute, and if anyone has questions beside that, please write them in the chat. So this cost estimation is something that the query optimizer would typically do in order to decide on the most efficient way for accessing a certain table. There doesn't seem to be any questions for the moment. All right. I think I can directly resolve it here. All right. So first of all, we typically want to estimate how many entries we can fit on a page in order to calculate cost. And that depends on the page size as well as on the entry size. Here we have 1,000 bytes per page, and each entry uses up 10 bytes, so we can fit 100 entries on each page. And since I have 60,000 students, and for each student I have 10 enrollments, that makes 600,000 enrollment entries, I can fit 100 of them on one page. So if I divide one by the other, I will end up with 6,000 pages. And since I'm simply scanning all the pages, and since I'm calculating cost as the number of pages accessed, that means that here I have a cost of 6,000 page accesses. All right. Now, perhaps some of you are wondering about why we don't count any cost for instance, writing the output of the operation back to hard disk or anything like that. Does anyone have an idea why we are not considering the output cost? So then please put it into the chat. Yes. Okay, some good propositions coming in here. Yes, okay, all of this are possibilities. Yes, exactly. So, I mean, in a way, the output cost essentially, okay, bottleneck is on the scanning. Yes, that is true as well. Yes. Okay, so all of those are great points. And also if you think about the way in which the cost information is typically used, typically you calculate cost in order to choose between different operations for the same query. Why doesn't it make sense to consider the output cost in order to choose between different alternatives? Exactly, yes. So in here, so all of those are great points, by the way. And I mean, perhaps the main reason in practice why we don't consider the output cost when using cost to compare different alternatives is that since all alternatives answer the same query, all of them must produce the same output. That is why the cost for processing the output is essentially a constant. And so that is why when calculating cost, we typically neglect any cost that is associated with the output that an operation is producing. All right, very good. Now, let's consider cost for the second alternative that we have seen. We have the same query, but this time we assume that our data is sorted by the course ID, and that is helpful because then we can do a binary search. So via binary search, we would essentially search for the first page containing the CS4320 entries, and then starting from there, we would scan all data in order of pages until we find the first entries that are not for CS4320 anymore. So again, I give you a minute before resolving the example. Here you have again the information on the upper half of the screen. We have the number of students, the number of courses. That information is new because now we need it, and the number of enrollments per student, again the size per entry and the number of bytes per page. All right, and here on the bottom we have already the number of entries that you can fit on a page. We have the number of enrollment pages. Now I would recommend you to first calculate the number of search steps executed by binary search, then to calculate how many pages we scan starting from the first page after binary search has been finished. And from that, you can quite naturally derive the total cost. I give you a minute to think about it. If there's any questions, please put them into the chat. All right. So even if you didn't have yet time to do all the calculations, perhaps you had some time to think about how you would do those calculations. And let me resolve this. So since we are executing a binary search, the number of search steps is given by the logarithm of the number of pages. So in each search step, you're looking at a page and you're deciding whether the entries you're looking for are located to the left or to the right of that page, basically. So in each search step, we are essentially dividing the range of pages that we are interested in by factor 2. And that means that if I want to find one page on 6,000 pages, then after 13 steps, I will have definitely narrowed it down to one single page. And then I know where I can start my scan. Now, the number of pages that we scan, that essentially depends on how many entries I have for the CS4320 course. Now, here the information that I have given you is that we have 100 courses. So we can estimate that if we have 60,000 students, 10 enrollments per student makes 600,000 enrollment entries. And if I have 100 courses, then I can assume that in average, I have 6,000 enrollments for the CS4320 course. And since I can fit 100 entries on each page, 6,000 divided by 100 is 60 pages. So assume that the result to this query contains 60 pages. And this is how many pages I need to scan after I have found the first page from which to start the scan via binary search. And then in order to get the total cost, you just have to count together the access cost for those two different phases of the algorithm. And then you end up with something which is already significantly cheaper than what we have seen previously. Now, one question to you would be where we have used simplification. I think I'm just going to answer that question for you. For instance, one way in which we have used simplification here is that we have assumed that we have the same number of enrollments for each course, because we simply said we have a total number of enrollments and we are dividing that by the number of courses to get an estimate for how many enrollments we have for the course that we are interested in. And that type of simplification is very commonly done in the context of query optimization, for instance. Once we try to estimate the cost of different alternatives, it is often not too far from the truth, but every once in a while it causes big problems. And we will talk more about the problems which are caused by incorrect cost estimates in the following. Here one question in the chat is why we cannot just do two binary search. I assume this means you are thinking of making one binary search to find the first page and one binary search to find the last page of the course that we're interested in. And that is a great point. The thing is this, we anyway have to scan the pages which are located between the first and between the last page, because those are the entries that we are actually interested in, and we have to read them from hard disk. And if we anyway have to scan those entries, we can essentially save the second binary search, because once we keep scanning entries, we will just notice that suddenly we find the first entries for a different course, and then we immediately know that now we can stop scanning. So we don't need a second binary search in order to find the end of the scan range. But it is a great question. Okay. All right. Now, in the following, I'm gonna we're gonna discuss more about cost estimation for indexes. We will also continue there for the next time, and we will see in practice how query optimizers make those cost estimates by a little demo. I'm quickly gonna introduce the next example, and if you're motivated, I encourage you to have a closer look and maybe try to figure it out yourself. You also have the solution in the slide, so you can find the solution there, but I encourage you to first give it a try to figure it out yourself. What I'm asking you here, that is to estimate the access cost with a tree index, which has the data integrated into the index. So that's a clustered index. And here we have some additional information given compared to the previous versions. For instance, here you see we have the index fan out, which is the number of child nodes that each node in the index has. And then I recommend you to estimate the total cost by calculating the number of inner nodes that you visit in the index, the number of leaf nodes that you visit in the index, because each node corresponds to one page access, and then finally to calculate the total cost. All right, so we have reached the end of the lecture. I hope you're having a nice day, and I see you again on Wednesday.